Hello, and thanks for joining us for this hopefully interesting talk on a coming new capability for NVMe over fabrics. My name is Rob Davis, and I'm from NVIDIA, and along with Doug Farley from Dell, we're going to explain to you how you will soon be able to boot across a network, attach computers with NVMe over fabrics. This capability is often called boot from SAM. So, Doug, let's get started. First, some background on the NVMe Express industry organization that was started many years ago to develop high-performance interfaces to SSDs. You may remember in the beginning, SSDs were connected to computers with SAS or SATA, like hard drives were. NVMe Express changed all that with an industry-wide standard interface for connecting them over PCIe that is ubiquitous today. That standard was then expanded to add support for connecting NVMe SSDs across a network. Later in the presentation, we're going to break down this standard in a little more detail, but it's also important to know that many markets across the IT industry have been impacted by this standard in a very positive way with its new capabilities. This slide shows the NVMe family of specifications. It's actually version 2. It includes a base specification, a command set, transport, and management. Those are the details that we're going to go into from the slide before. And the boot is actually going to become a new member of this family with its own specification. So why did Dell, NVIDIA, and many other companies, Intel, Red Hat, HPE, VMware, SUSE, and others, work to make this new capability happen? Frankly, it is because this is a missing capability that NVMe over Fabrics needs to take its place as the leading technology for networking storage. It allows a standardized, meaning multi-vendor, way for you to boot your computer from an OS image stored on the other side of a network. This is critical for large deployments for many reasons. Think about this example, the difficulty of upgrading the OS in a data center with even 100 computers. Instead of having to push a new OS or even patches to all those machines, with NVMe boot, you just do it in one place. And this is only one of the many values this technology brings. The goal of this new boot specification is to standardize booting from NVMe and NVMe over Fabric namespaces. NVMe is in fact already widespread for booting on the PCIe transport. What's new is, of course, over Fabrics boot, and it is different from other remote disk boot technologies because it is fabric agnostic, like NVMe over Fabric standard is. You can boot. It has boot support for all NVMe over Fabric transports. It is low. It also has many advantages over other technologies in that it's lower latency due to the efficiency of the NVMe command set, and it's scalable through the new NVMe over Fabric's discovery capabilities.
Hey, Rob, let me take this one. So the NVMe boot standard ultimately defines constructs and guidelines for booting from the NVM Express interfaces over its supported transports. As we previously said, the NVMe boot specification will become part of the family of NVMe specifications. This initial version defines the extensions to the NVMe interface for booting over the NVMe over TCP transport. In addition to that, the normative section includes content that describes the generic requirements for information sharing and provides domain-specific mechanisms like ACPI tables to enable the pre-OS and OS drivers to share their configuration context. In addition to the normative content is an informative section that covers concepts of pre-boot configuration mechanisms and best practices. Mechanisms that provide OS consumption of that pre-boot configuration, other OS-specific best practices, and fabric specifics such as interfaces, transport interface definitions. A boot specification is comprised of more than one standard and requires the cooperation of multiple ecosystem partners. In addition to NVMe, we develop specification content for ACPI and UEFI, as well as a public reference implementation. In order to speed the development and standardization of booting from NVMe fabrics, we chose to start from the TCP transport and follow the groundwork laid by iSCSI. This included adopting a similar boot flow handover mechanism as iSCSI used. iSCSI used an ACPI iSCSI boot firmware table as its mechanism to share pre-OS configuration with the OS. NVMe developed a similar mechanism called the NVMe boot firmware table. For NVMe fabric, booting the UEFI environment, boot starts with the security and PEI phases. NVMe fabric boot introduces new functionality in the driver execution environment, or DIXI. This includes that namespaces used for boot devices are discovered from the information stored during configuration, and that the driver connects to NVMe fabric subsystems and discovers namespaces that are present for OS boot. DIXI is followed by the boot device selection phase, or BDS. BDS is when namespaces that can be selected as a final boot device are present and enumerated. Lastly, BDS is followed by the transient system load phase, which is where the OS image for the boot device is loaded and UEFI to OS execution handover is performed. At this point, the NBFT has been generated and is accessible to the OS. During runtime, now that the OS can be loaded, there are two common use cases: installation or normal OS operation. The OS or user may choose to use the NBFT data or its own existing configuration in order to reestablish connectivity to devices configured during the pre-OS environment. The NBFT is a mechanism to hand off configuration data to the OS. The pre-OS administrator configures information such as subsystem NQN, IP address, namespaces, and security-related info. This information is then presented to the OS via an ACPI table called the NBFT. As you can see in the upper right diagram, the NBFT consists of three major elements: a header and control descriptors, descriptor lists that include relevant host, remote, NVMe fabric controller information, and detailed structures that define the elements and properties of these descriptors. At this point, we now have all the information the pre-OS environment needed to complete network boot and are ready to transition to the OS runtime. As mentioned previously, reference implementations are necessary in order to aid developers across the industry in enabling this new NVMe fabric capability. In the pre-OS, a new UEFI driver for the TCP transport for EDK2 was developed and will be made available. On the OS boot and runtime, a Linux reference implementation that exposes the NBFT and consumes the content of the NBFT will also be made available. With this, common OS tools may then be used. This diagram shows where the design for a reference implementation evolved from our initial concepts to the yet unpublished reference implementation. In the light green on the left, we plan to leverage existing ecosystem components and develop new core elements specific to NVMe fabrics, as seen in blue. In particular, we set out to reuse the existing robust implementation of NVMe fabrics from SPDK and leverage that in our EDK2 driver. On the right, as the reference implementation evolved, we were able to contain many of the NVMe fabric specifics that were adopted from SPDK into an EDK2 library, as seen in green. From there, we were then able to build an extensible EDK2 driver framework around those interfaces, seen in brown, that reuse much of existing UEFI interfaces that are available to us today. For a runtime and Linux reference implementation, there are three primary layers of concern: platform, kernel, and user space. The new work, as shown in green, for supporting this reference implementation is focused primarily on user space and leveraged the existing ecosystem infrastructure shown in blue. In the middle of the slide, the Linux kernel exposes the NBFT from ACPI via sysfs to user space. From there, user space tools, starting with extensions to libnvme and NVMe-CLI, allow for exporting and consumption of the content from the NBFT. Systems management tools like Drakit, UEFI Boot Manager, Systemd, and others can then get standard representations from NVMe-CLI and use those for NVMe over Fabric configuration and/or reconnection as normal. Without ecosystem cooperation, the standardization of NVMe over Fabric's boot would have not been possible. Just to reiterate, the ecosystem partner contributions were messaging interfaces for the UEFI system spec, ACPI table creation, Tiano Core as the host for EDK2 reference, DMTF Redfish for security configuration, the Linux kernel and user space community for all their work in enabling NVMe over Fabrics, and lastly but not leastly, the NVM Express board for all their unwavering support for this effort. As previously stated, numerous work products were created in the development of the standard. The results of the NVMe over Fabric boot specification include the following specification materials and reference items as listed here. The location for these will be available on the last slide of this presentation. And finally, a call of action to the industry. Our work here cannot stop. We would like to call out for help from the UEFI community to add and improve on the EDK2 driver. We would like participation from the NVMe community to add and enhance support for all of our transports. We also need the industry to implement BIOS support in all interested products. And lastly, OS and installer support to implement NVMe over Fabric's boot to enable NVMe over Fabrics to take its place as a full-featured storage network solution.
Great finish, Doug. Together, we both want to thank you all for listening to this talk, and we look forward to working with you as we bring this new technology to the world.
Thanks, Rob. Everyone, have a great rest of your day, and thank you for coming.